Hi. Thanks for taking a look at my YouTube video. I have put together this video with info on blowers in general, but before I start the video I wanted to say I built my Blown 671 IROC-Z about 15 years ago. I used a small block 305 and bored it out, then blueprinted and balanced the whole motor. Replace crank, cam, fuel system, and such. Then added a dual carb manifold. The manifold was made by Offenhauser. I also added two 750cc Holley double pumpers, upgraded fuel system to electric high output fuel pump. Then upgraded the cooling system with a new radiator. Also added dual electric cooling fans. I had most of the work done in New York by Jim Audi Race Cars, on Bullis Road. Bunch of work, but once it was done it was 100% streetable Pro Street IROC-Z. So I figured I would put together some info on blowers. This is info I have gathered over the years. Once again thanks for viewing and enjoy my YouTube video and videos by Custom Channel. There are currently 3 basic types of superchargers being sold in the performance market today: the Roots type, centrifugal, and screw type. We'll use the terms supercharger and blower interchangeably. The centrifugal supercharger is very similar to a turbocharger, except the centrifugal supercharger is driven by a belt off the engine, while the turbocharger is driven by the force of the exhaust gases. These type of superchargers, or turbos, run at extremely high speeds. To achieve these high speeds in the centrifugal supercharger, there is an additional internal step-up drive inside the blower. Due to the design of these units, the faster the impeller spins the more boost the blower makes. As a result, these units typically do not produce much power at low engine speeds because the impeller is not spinning fast enough to make much boost. If it were even possible to gear the blower so that it would spin fast at low engine speeds, it would then make too much boost at higher engine speeds. Turbos employ a device called a wastegate, which bypasses exhaust gas past the turbo when a certain boost limit is reached. The screw-type blower appears somewhat similar to a Roots-type blower from the outside, but the internal rotors are quite different. In a screw-type blower, the rotors interleave one another, and as the outside air is drawn into the blower, the rotors progressively compress the air inside the blower as it passes along the rotors. These rotors require an extremely high degree of tolerance and, as a result, the screw-type supercharger is more expensive than a Roots. The Roots blower is the simplest of all blowers and therefore is also the least expensive. A Roots blower does not compress the air inside the supercharger. It is actually an air pump. The compression of the inlet charge, creation of boost, actually takes place in the cylinders and the manifold. Centrifugal superchargers and screw-type superchargers are called internal compression blowers because the air compression takes place inside the supercharger. Roots superchargers are external compression blowers because the air compression takes place outside of the supercharger. Roots-type superchargers first appeared in automotive applications as far back as the 1930s. Roots blowers have been used on GMC diesel engines for many years. In the late 1950s, what a supercharger does: an internal combustion gasoline engine draws in air which is mixed with gasoline. This fuel, air charge is drawn into the cylinders as a result of the vacuum created when the piston travels down the cylinder. When the piston goes back up, this fuel, air charge is compressed to a fraction of its original volume. If an engine has a 9:1 compression ratio, the fuel, air charge will be compressed to 1/9 of its original volume. When the spark plug ignites this compressed fuel, air charge, the resulting combustion causes an expansion of the charge which forces the piston down. As you pack more fuel and air into the cylinder, the combustion charge becomes more powerful and the engine produces more power and torque. In an unblown engine, when the piston goes down on the intake stroke, atmospheric pressure tries to fill the void now present in the cylinder. If the cylinder filled completely with air, the engine would have a volumetric efficiency of 100%. Due to the restrictions in any engine created by the air cleaner, cylinder head and cam timing, all of the air that should get into the cylinder can't, so the typical engine's volumetric efficiency is less than 100%. By removing these restrictions, or at least reducing them by improving the cylinder heads and cam timing and using a larger carburetor, the volumetric efficiency of an unblown engine can be improved. With a supercharger, the amount of air and fuel that can be packed into the cylinders greatly exceeds the 100% volumetric efficiency of a highly refined unblown engine. Since the air is now being forced into the engine, you can put a substantially denser fuel, air charge into the cylinders. On most street-type blown applications running 6 to 7 pounds of boost, approximately 40 to 50% more fuel and air can be packed into the cylinders than in a comparable unblown engine. The reason that larger displacement engines make more power and torque than smaller ones is that more fuel and air are available for combustion. As a result of supercharging, a small displacement supercharged engine can produce similar horsepower and torque to a naturally aspirated larger displacement engine. With a Roots blower, the carburetor functions basically the same as it would on an unblown engine, except it now sits on top of the supercharger. Although this is somewhat of a simplification, you can think of a Roots supercharger installation as removing the carb and intake manifold from the engine and reinstalling the blower and blower manifold in its place and then bolting the carb on top of the blower. Then a belt is attached to pulleys on the blower and the crankshaft to turn the supercharger. Explaining boost. Boost is the amount of air pressure created by the supercharger. Supercharger boost is largely misunderstood, even by some experienced performance enthusiasts. The air ratio of the supercharger is consistent with the engine displacement. Supercharger boost, however, is not totally constant. This is because at lower blower speeds, the clearances between the supercharger case and the rotors allows for air leakage with some loss of boost efficiency. If your engine is not as free-breathing as it could be, because it has a stock or low-performance cam, small valves, restricted ports, etc., you will typically see the boost readings go up in the higher RPM ranges. This is because the boost the blower is making cannot fully get into the cylinders due to these restrictions, and the boost pressure starts building up in the manifold, which is typically where the boost readings are taken. Therefore, artificially high readings will be observed. Interestingly, this means a supercharged engine can make more power with lower reading on the boost gauge. Boost is a function of three things: the displacement of the engine, the displacement of the blower, and the speed that the blower is turned in relationship to the engine speed. There are a few basics to remember. Assuming a constant speed ratio between the engine and the blower, a larger blower will make more boost than a smaller one on the same size engine. As engine size goes up, boost goes down if the blower speed and blower size remain constant. Conversely, as engine size goes down, boost goes up. On a given size blower and a given size engine, boost can be increased by running the blower faster in relation to the engine speed, overdriving, or it can be decreased by running it slower, underdriving. As a very rough rule of thumb, you typically want to run larger blowers on larger engines. However, there is no reason you can't run a larger blower on a small engine, such as a 671 on a small block 327, as long as you adjust your drive pulleys to get the blower to run slow enough to keep the boost down to a level that is appropriate for the compression ratio you are running. Conversely, it is not practical to run a small blower on a big engine, because you would have to turn the blower so fast to make a reasonable amount of boost that the blower would become very inefficient, particularly at higher engine speeds. When Roots blowers are turned at very high speeds, they actually can heat up the inlet air to such an extent that the air expands substantially. This overheated expanded air loses so much density that even though your boost gauge says the blower is making boost, in reality you aren't putting any more air into the engine than an unblown engine would get. Running the blower very slowly in relation to engine speed, such as would occur in our example above of a 671 on a 327, would result in inefficiencies at lower engine speeds. A slow-turning blower, especially a larger one like a 671, would have a lot of low-speed leakage of boost pressure past the clearances between the rotors and the blower case. This leakage reduces low-speed boost pressure, with a resultant decrease in the amount of additional power produced. This is why it is important to have a blower that is sized in relationship to the engine displacement. In this instance, if the blower pulleys were selected to make decent boost at low engine speed, you would end up with excessive boost at higher engine speeds. Additionally, keep in mind that the larger the blower, the more potential for low-speed boost leakage to occur because the total clearance path is much longer on a larger blower. Many people assume a blower is making boost 100% of the time. In actuality, the blower normally only goes into boost when the throttle is opened substantially or when the vehicle is under load, such as going up a steep hill or pulling a trailer. In order to make boost, the blower must get air, and during most driving you will only have the throttle open a slight amount. Interestingly enough, even when not making boost, the spinning rotors improve the volumetric efficiency of the engine to the point where you can maintain high cruising speeds at lesser throttle openings, and in normal driving around town, you will notice that the vehicle is much livelier even when not making boost. This phenomenon can improve gas mileage under certain circumstances, although typically on an overall basis fuel economy will decrease about 3%. This isn't much of a factor. If your car was getting 20 miles per gallon before the blower, that means you will be getting 19.4 miles per gallon after the blower installation, but with a 40 to 50% increase in horsepower. 671 and 871 supercharger come with drive ratios that will typically produce 5 to 7 pounds of boost. These boost levels are based on 350 or 454 SID engines. The 1071 through 1471 supercharger kits come with drive ratios that will produce 5 to 8 pounds of boost. These levels are based on a 502 SID engine. See our additional drive ratio charts at the end of this section. If your engine is smaller than this, your boost will be higher. If your engine is larger, your boost will be lower. Your boost will fall within a particular range, such as from 5 to 8 pounds. Because a lot of factors can cause boost to vary. Depending upon how well your engine breathes, the amount of observed boost on a gauge can vary substantially. If you install blower and your observed boost comes up on the low end of our estimated range, it means you have a really good breathing engine. Another factor that can contribute to low boost is a restricted air inlet or too small of a carburetor. Remember that at full throttle your engine is going to need about 50% more air than it did before the blower was installed. Are your air cleaner and carburetor capable of letting in 50% more air? If not, you won't make the boost that the blower is capable of. The amount of boost that can safely be run is primarily determined by the compression ratio of your engine and the gas that you are using. As a basic rule of thumb, the 5 to 8 pound boost range that is provided by the standard pulleys supplied supercharger kits is suitable for compression ratios in the 8 to 9 to 1 range when used with 92 octane gasoline. If your compression ratio is higher than this, you will have to run less boost. If it is lower than this, you can run more boost. The key to any supercharger installation is that detonation must be controlled. Detonation in a blown engine is more destructive than in an unblown engine, and damage to piston ring lands, or worse, will occur if you continue to drive a blown engine that is detonating. Many enthusiasts will experiment with increasing the boost until detonation occurs and then back down to the last boost level achieved without detonation. This requires purchasing additional optional pulleys. Remember that rarely are any two modified engines similar in how they react to boost and compression ratio combinations, so don't expect to copy what someone else may have done and achieve a successful installation. Unfortunately, as in many aspects of dealing with modified engines, trial and error is about the only way to achieve your ideal combination. Compression ratio, boost pressure. The compression ratio of your engine has a direct relationship to how much boost you can run. If you have a high compression ratio, such 9.5 to 1 or 10 to 1, you will only be able to run a small amount of boost. The compression ratio that is built into your engine is called static compression. When you combine the boost you are running in conjunction with your compression ratio, the result is known as the effective compression ratio. Formulas have been developed that convert your static compression and supercharger boost to the effective compression ratio. Experience has shown that if you attempt to run more than about a 12 to 1 effective compression ratio on a street engine with 92-octane pump gas, you will have detonation problems. To some degree, this can be controlled with boost retard devices, but it's not recommended that you set up your engine and supercharger to provide more than a 12 to 1 effective compression ratio. Please note that all engines differ in their tolerance to detonation. Note you should be able to adjust this with the correct ignition system. If you are building your engine from scratch, it is a good idea to try to build it with a relatively low compression ratio, such as 7.5 or 8.0:1. It is fairly easy to change the boost to get the best combination of performance and power, but it is extremely difficult to change the compression ratio, especially if you want to lower it. Additionally, you will make more total power with a low compression, high boost engine than you will with a high compression, low boost engine. In selecting the proper supercharger for your application, you also need to take into consideration how you plan to drive your vehicle and the approximate boost level desired. How you plan to drive your vehicle is important because you can set up your blower to be more efficient at high engine speeds or more efficient at low engine speeds, or you can arrange for the best compromise for the full engine RPM range. For example, if your vehicle typically will be driven at speeds under 4,500 revolutions per minute and will never, or infrequently, you may want to select smaller blowers. A smaller blower can be driven at a higher speed, which will produce a substantial amount of boost, particularly at lower engine speeds. However, this high blower speed will be less effective at higher engine speeds due to the overheating of the inlet air as discussed earlier. Conversely, if you choose a larger blower for this same application, in order to achieve the same boost level, the larger blower will have to be turned at a relatively slow speed. This combination will not produce the low-end power that the faster-turning small blower will, but will significantly outperform the small blower at high engine speeds. However, if you never drive your vehicle in the higher speed ranges, you may be giving up impressive improvements in the lower speed ranges. You may choose to do this anyway because you want the look of the larger blower and are willing to give up some bottom-end performance. Supercharger rotors. Two lobe rotors feature thick wells and a solid shaft, which prevent flexing at higher boost levels. The supercharger case is smaller because the two-lobe rotor design takes up less area in the case. This allows for a more compact package for easier underhood installation in many applications. Larger superchargers use three-lobe helix rotors. The helix-style rotor was developed by General Motors for larger GMC superchargers. They are more efficient than a two-lobe rotor because they use less horsepower to supply a greater volume of cooler air charge to the cylinders. Helix rotors also resist flex under extremely high boost situations. These superchargers use larger cases, allowing for a greater volume of air displacement per rotor revolution. There is also a version of the three-lobe helix rotor used in racing called the Hilux rotor. This design has even more twist imparted into the blower rotor and does provide more power. These blowers were developed for alcohol dragster and funny car racing and are extremely expensive, making them impractical for anything but professional racing. The increase in performance is not justified by the increase in cost for street applications. Expected performance increases. Installing a blower is one of the easiest ways to substantially improve a vehicle's overall performance. With one of superchargers, here are some of the improvements you can expect. 1. Improved starting. A properly set up blown engine typically will fire instantly, usually before the engine has even made one revolution. This is because the blower immediately is pushing the inlet charge right into the cylinder, rather than waiting for the engine vacuum to draw the charge into the cylinder. 2. Substantial increases in bottom end performance. While this is true with all blowers, it is particularly attributable to the smaller ones. 3. Substantial horsepower increases. Bolting one of ProStreet superchargers on an otherwise stock small block Chevy will result in an increase of approximately 100 to 120 horsepower. Usually with a mild blower cam and a larger carburetor, you can expect a typical small block to produce anywhere from 360 to 400 streetable horsepower. The addition of a set of good heads can boost this into the 440 to 470 horsepower range. Torque on an engine of this type typically will be in the 400 to 440 foot range. All of these figures are based on a blower that is producing about 6 or 7 pounds of boost. A larger blower, such as 671, on a similar engine to the one described above could push the top power output well over 500 horsepower. Note, it is important to understand that for all practical purposes, an engine does not know what size supercharger is bolted to it. The amount of boost that is being produced by the blower is the critical factor. So our power output estimates above are somewhat typical of any of blowers, with the following exceptions. At very low engine speeds, the smaller blowers will typically produce more torque than the bigger blowers. At very high engine speeds, the larger blowers will produce substantially more power than the smaller blowers. Other engine modifications. One of the big advantages of a supercharger is that it can overcome many induction deficiencies in an engine, especially in the low to mid-range RPM area. ProStreet and 671 superchargers can be installed on a stock engine, as long as the static compression ratio is 9:1 or less and engine speed is limited to 6,000 revolutions per minute. Most stock engines are equipped with cast pistons, cast crankshaft, 2-bolt main caps, and a small camshaft, requiring you to run very low boost pressure of 3 to 5 pounds maximum. Higher boost levels will cause detonation and engine failure. To run boost levels from 6 to 10 pounds. Forged blower pistons with a static compression ratio of 7.5 to 1. Steel crankshaft. 4-bolt main caps. Steel harmonic dampener. Stainless steel valves. 3-angle valve job. More aggressive camshaft. Roller rockers. Ported and polished heads. Steel rods with good rod bolts. Chromoly push rods. High output ignition. High flow water pump, cast iron or aluminum. Minimum of a 2/2 diameter dual exhaust with headers. Recommended primary tube diameters and collector sizes are: small blocks, 1/5/8 to 1/3/4 with 3 inches collectors. Big blocks, 1/7/8 to 2 with 3/2 collectors. For maximum boost and horsepower applications, 12 pounds or more. High quality forged or billet crankshaft. 4-bolt main caps with quality bolts or studs. Steel harmonic balancer or crank hub. High quality steel rods, H or I-beam. Forged blower pistons. O-ringing the block, mandatory. Severe duty stainless steel valves or Iconel. Fully ported and polished heads. Solid or roller cam designed for high boost. Roller rockers. Chromoly push rods. High output ignition management system or a magneto. Blueprinted carburetors or fuel injection. High octane race fuel, 112 plus rating. Minimum of a 3 inches diameter dual exhaust with free-flowing street, race mufflers and large tube headers. Recommended primary tube diameters and collector sizes are: small blocks, 1/7/8 to 2 inches with 3/2 collectors. Big blocks, 2/1/8 to 2/1/4, with 4 inches collectors. Maximum effective compression ratio on gas not to exceed 24 to 1. It's important to realize that there are no hard and fast rules. Carburation with a blower. Choosing a carburetor is a very important step in building a blower motor. Under boost, the engine could need up to 40 to 50% more fuel and air, so it's key to pick a carburetor that is up to the task. If your carburetor can't provide enough fuel and air, you can't take full advantage of your supercharger and you won't be able to make maximum boost. In addition to providing fuel for the motor, the carburetor also is the restriction through which air must pass to get into the blower and the motor. Running too small a carburetor therefore means that you can't flow enough air to produce maximum boost. It's very simple: if a supercharger can't draw the air and fuel into it, you can't get horsepower out. Myself, for my IROC Z, I use two 750cc Holleys. The amount your carburetor needs to flow depends on engine characteristics and on the amount of boost your blower will be making. There's a formula for determining the required carburetor CFM. I used 750 CFM Holleys. If your carburetor is too lean, it will cause detonation, which can destroy your motor. How do you know if it's too lean? You'll have several obvious indications, like glowing red headers, audible lean pop, or engine surging. Even if you don't experience these conditions, you should still read your spark plugs for proper color. You want to see a medium to dark tan color. If you run one or more Holley carburetors, be aware that they contain power valves. Power valves provide additional fuel when there is no vacuum at the base of the carburetor. However, in a blower application, there will always be some vacuum, so the power valves will not function properly. You will need carburetors that have a boost-referenced power valve circuit. Holley supercharger carburetors are specifically designed with this feature. In addition, they also are 100% wet-flowed, equipped, and calibrated for the special needs of a supercharged engine. Ignition systems with a supercharger. I used MSD ignition, but many street supercharger applications will work fine with the stock ignition system. Because blown engines make so much low and mid-range power, it is not necessary to rev to high RPMs. High-performance ignitions are primarily required to provide adequate spark at higher than normal RPMs. If most of your driving is going to be under 5,500 revolutions per minute, you probably won't need an aftermarket ignition. For optimum performance at higher engine RPMs, select an aftermarket performance ignition system. It is usually a good idea to run spark plugs that are 1 to 2 ranges colder than normal with a blower. The more boost, the colder the plug required. Colder plugs will foul easier than hotter plugs, so in this instance a hot ignition may be advisable. The main thing that needs to be addressed with a blower is to make sure that detonation is controlled. A handy device to have is an ignition system with a boost retard control, such as the Holley ignition. With the use of this unit, you can run normal timing settings which will allow for easy starting and reasonable fuel economy under normal driving situations. However, when you step on the gas and the engine goes into boost, this timing setting may cause detonation. With the boost retard control, the driver can dial in ignition retard with a dash-mounted knob. These devices usually operate on a degrees of retard per pound of boost and are typically adjustable from 1 degree to 3 degrees of retard per pound of boost. As an example, if the unit is set to deliver 1 degree per pound of boost, that means that when your blower is putting out 4 pounds of boost, the distributor will automatically be retarded by 4 degrees. When you reach 7 pounds of boost, it will be retarded by 7 degrees. Best results are achieved by driving the vehicle under boost and adjusting the unit until any detonation is eliminated. It's not recommended using these devices in marine applications. Retarding the timing under boost increases the combustion temperatures. On a street vehicle, this typically occurs for short periods of time. In marine applications, the engine is usually in full boost all of the time. As a result, these prolonged high combustion temperatures can burn pistons or valves. Most blown engines operate best on 28 to 34 degrees of total timing. Running more total advance will not provide any performance increase. Your distributor should have a centrifugal advance mechanism that has been set up so that the entire advance is in by 2500 revolutions per minute. The best way to set your timing is to put a permanent mark on your harmonic damper that represents 34 degrees total advance. If your damper doesn't go this far, you can measure the timing marks on your damper and then, using your measuring tape, calculate where 34 degrees would be. 34 degrees is a very safe figure and should provide close to optimum performance. After you mark off 34 degrees, start your engine and rev it up to a speed where the entire distributor's mechanical advance will be in. This should be somewhere over 2500 revolutions per minute. Then read the new 34 degrees mark like you would read TDC at idle speed. Adjust the distributor so that the new mark on the damper lines up with the 0 on your timing tab. This would provide 34 degrees of total timing, or if you wanted 32 degrees of total timing, you could line up the mark on the damper with the 2 degrees ATDC mark on the timing tab instead of 0. Supercharger engine camshafts. The choice of camshaft can make or break a blower motor. A legend in the industry, Lunati offers several camshafts specifically designed to work with blower kits. In addition, the following are a few basic guidelines for selecting the proper cam for your motor. Obviously, the amount of boost your supercharger produces is going to be a factor in choosing a camshaft. The mildest of blowers are the Pro Street superchargers, which are set to produce from 5 to 7 pounds of boost. It's suggested a hydraulic cam for these applications, where the engine will not be spun past 6,500 revolutions per minute and has several grinds available. Keeping the cylinder pressure up also gives you excellent throttle response. The milder cams are great for street performance enthusiasts who want to gain about 100 to 120 streetable horsepower. For 671 and 871 blowers again recommends running a hydraulic cam, as long as you keep the boost level below 10 psi. Also offers cams for these type of applications. For your higher boost levels, which includes all 1071, 1271, and 1471 applications, in gasoline-burning engines, I would suggest running a flat tappet or roller cam with a 110 degrees lobe center line. This cam design provides good overall power on pump gas and also aids in engine cooling. Plus, the 110 degrees center line provides even sharper throttle response and helps lower initial cylinder pressure. You won't miss the cylinder pressure with these blowers, since they make plenty of boost. Conclusion: supercharging is an extremely effective way to reliably increase horsepower and torque, particularly in the low to mid RPM ranges where most street machines are operated. Unfortunately, due to the wide use of superchargers in drag racing, many people think a supercharger is an exotic race component and is not truly suitable for the street. Now that supercharging is becoming quite common on stock factory vehicles, more people are realizing that a supercharger is a safe, practical source of performance increases.